Okay, I think I'll start. It's my pleasure to introduce our guest for today, Giray Yağlıkçı, who is now a postdoc at ETH. He started his bachelor and master studies in Turkey at Top University, near Ankara or in Ankara.
Yes, in Ankara, yes.
And afterwards, he went to the US and did a master's at University of Notre Dame in Indiana.
That's true. Yeah, correct.
And actually you started working with Onu as well. Onu Mutlu in the US, you told me.
That's true, yes.
And then when Onu Mutlu went to the ETH, I went with Onu to the ETH, and essentially then did his PhD at ETH, finished last year, and is now a postdoc in Onu's group. So Giray is working on a very exciting area that we don't see too often, and I think we are not doing so much at CISPA so far, which is really system security on a kind of hardware, low-level hardware level, in particular for memory controllers, how to build secure systems, how to analyze the security and properties of real-world hardware controllers, memory controllers, and the publishing also at venues, not only tier 1 system security venues, but then also other venues like Micro and HPCA.
Sure.
You told me, DSN as well, and so on. Mm-hmm. So I'm really looking forward to this talk. Please take it away, Giray.
Thank you very much for the introduction. So today I'll talk about scaling systems robustly and sustainably. Before talking about that, of course, I need to define what I mean by scaling. So when I say scaling, I mention scaling in two aspects. The first one is scaling down the manufacturing technology node size, essentially making our chips denser, putting more transistors in our chips or more bits in our chips. That gives us higher performance and lower energy consumption going forward, but they come at the cost of circuit level failure mechanisms that I will talk mostly about. And once you want to mitigate such bit flips or such failures, you end up having high hardware complexity, energy consumption, or reduced availability. The second aspect of scaling out systems in a distributed manner. This is important for lowering the cost of ownership and enabling dynamic scaling on demand. So these are really important features that we want to have in our systems, but it also comes with security and privacy concerns that might increase our overheads and prevent us from achieving the full potential. So with these problems in mind, my goal is to enable systems scale robustly and sustainably as chips get denser and many users share systems. So this is my journey towards robust and sustainable scaling. I started with studying the memory access latency and energy consumption for achieving more sustainable systems. And in my PhD, I focused on this particular problem in today's commodity memory chips called read disturbance. And then later on, I focused on availability of data and resources while mitigating such failures. And I'll also talk about some future research at the end in 3 different directions that I'm planning to pursue. So let's start with my studies during my PhD. So I'll start with this concept of memory isolation. So let's say this is your memory, and you perform an access to your memory, and you see a bit changing from 1 to 0 or 0 to 1 in a different location that you didn't access. So you do not want this to happen in your system because it can lead to data loss or corruption. It can compromise your application's correctness. It can be exploited to leak private information or even take over your system. This is essentially a data integrity and confidentiality issue when this happens. And as a rule of thumb, we need to ensure that an access to a memory location should not affect other data in other addresses. And this is called memory isolation, and it is difficult to satisfy in modern DRAM chips, modern memory chips today. And here is why. Today, as the prevalent memory technology, we use dynamic random access memory, or in short, DRAM. And DRAM, this is how a DRAM cell looks like. So DRAM stores data in the form of electrical charge on a capacitor, and you access it through an access transistor. And it's a volatile memory technology, so it leaks charge over time, and you might lose your data after some time. So you need to periodically refresh this, meaning like you read and write back the data. And as you scale these cells to smaller sizes, this DRAM read disturbance phenomenon occurs. When you access a DRAM cell, your access creates some interference on the physically nearby cells and exacerbates their charge leakage. And as a result, you lose charge faster. So this is a cartoonish picture of how we organize our DRAM cells. So inside a DRAM, this structure is called DRAM subarray. We organize DRAM cells in a two-dimensional array and internally access them in a row granularity. So let's say we want to access a piece of data that is stored in row 2 here. We first need to open row 2 so that we can access data inside this. And then once we're done with data here and we want to access another piece of data, we need to close this row 2. So over an extended period of time, if you do this open and close operation many times, you see bit flips in physically nearby rows. And these rows might be owned by the system itself or some other users, or it can store your code, your data, and essentially it's creating some trouble for you and for other people in your system or for the system itself because it breaks the memory isolation principle. Okay, so we call the row that we keep hammering or opening and closing the aggressor row, and the other rows that are affected as victim rows. So to prevent such bit flips, there's a very simple method. If you identify that row 2 is being opened and closed very frequently, and you go and refresh the physically nearby rows, meaning that you open, read the data, and write it back, then you prevent all these bit flips. But it's easier to say than to do. And here's why. So with technological scaling, DRAM cells get smaller in size and they get close to each other. So all these effects are getting exacerbated. And if you look at the data from the field, these are all like papers published in CISPA, a top venue in computer architecture. We observed that the minimum number of times that you need to open and close a row to induce a bit flip got reduced by more than 2 orders of magnitude in the last decade. So DRAM cells are becoming increasingly more vulnerable to read disturbance. And as a result of this, we have some solutions. We had some solutions in the beginning, but they become prohibitively expensive because they need to perform these operations more aggressively, and they even become ineffective going forward. And we need more efficient, scalable, and comprehensive solutions to DRAM read disturbance. So with this motivation, what I did during my PhD is in twofold. First one is that we built a detailed understanding of DRAM read disturbance. For that, we looked at DRAM read disturbances sensitivity to different aspects like temperature, memory access patterns, victim cells physical location inside DRAM chip, and voltage that we provide to the DRAM chip. And the second part is devising novel solutions, leveraging insights into DRAM chips and memory controllers. For that, we looked at methods of leveraging the heterogeneity within a DRAM chip. We did our best to parallelize the preventive actions with dynamic accesses to reduce their performance overhead in the system level. And we also explored solutions that throttle some unsafe accesses to achieve a better, comprehensive, and more performant solution. So I don't have time to talk about all of these, so I cherry-picked some of them, and I'll talk about them. So I'll first talk about temperature. So this is first methodology, of course. This is the infrastructure that we use to test our DRAM chips. So you might notice that there's an FPGA in the middle. It's a Alveo board, but this infrastructure supports multiple FPGA boards. We program it with our own design called DRAM Bender, and we plug in a DRAM module to this FPGA board, and we connect this FPGA board to a host machine, and we clamp this DRAM module with heater paths from both sides. We press them to the chips, and we control the heater paths using a commercial temperature controller. And on the side, we also have a power supply that allows us to play with the voltage level on certain power rails. So with this infrastructure, we have fine-grained control over DRAM commands, timing parameters, temperature, and voltage. In this study, we tested 272 DRAM chips that implement DDR3 and DDR4 standards from 4 major manufacturers that cover around like more than 98% of the market share. To do our tests, we did our best to prevent sources of interference in a regular system. For example, we disable the regular refresh operations to not have any variation in our timings and to avoid refreshing our victim rows. We disable some calibration events and keep our tests really short so that our tests work reliably, but we are not interrupted. And we use the known worst case access sequence. Later, we redefine the worst case access sequence, but I will come to that later. Okay, so let's look at our first findings on read disturbances sensitivity to temperature. So in this study, we sweep temperature from 50 degrees Celsius to 90 degrees Celsius. Excuse me. And while we do this sweep, we observe a lower bound and an upper bound of temperature. In between, we observe bit flips in a given DRAM cell. And we do not observe any bit flips out of this region. And we call this range as vulnerable temperature range because the DRAM cell is vulnerable to read disturbance only in this temperature range. And when we look at many cells, basically, we observe that the vast majority exhibit this kind of behavior. And these lower and upper bounds change quite a bit that I will show next, showing that there's a strong variation across DRAM cells as well. So in this study, we did a hammer count of 150,000 activations here, quite large, basically. And here in this plot, we see a population density. So on the x-axis, I put the lower bound, and on the y-axis, I put the upper bound. And for a given data point here, we see the fraction of vulnerable DRAM cells that fall into that, between that lower and upper bound of vulnerable temperature range. For example, if you look at this point, 4.3% of the vulnerable DRAM cells are vulnerable to read disturbance between 50 degrees and 60 degrees, but not above 60 degrees or below 50 degrees. So we see that different DRAM cells are vulnerable to row hammer within specific temperature ranges. And this has an immediate implication on your system if you want to make sure that your DRAM cell is vulnerable to row hammer or not, or read disturbance. Basically, you need to test that DRAM cell at each possible operating temperature. That significantly increases your testing cost. That was the analysis in a DRAM cell granularity. Now we look at the same data in a DRAM row granularity. So on the x-axis, we sweep temperature from cold to hot, from 50 degrees to 90 degrees Celsius. And on the y-axis, we see the variation in bit flip counts per DRAM row. So this is not a very surprising result. Usually, your electrical systems go less reliable as you heat them up. And this is what it shows. When you increase the temperature, you have more bit flips in a DRAM row granularity. So this is data from one manufacturer, which is Micron. And when we look at the same data from 4 manufacturers, 3 of them, Micron, SK Hynix, and Nanya, are showing similar trends, whereas manufacturer B, which is Samsung in this case, is showing opposite behavior. So you heat up the DRAM chip, and things get better. You get less vulnerable to DRAM read disturbance. And this is just an empirical observation in this study. So we looked at the literature to understand why this happens. And we observed that it's a similar behavior to trap-assisted charge leakage model that is proposed in some earlier paper in the field. Basically, here what we see is that we sweep temperature on the x-axis from left to right. And this is some circuit level simulation study that models different charge trap models and shows that the minimum minimum number of row accesses to induce bit flip or row hammer threshold on the y-axis is getting low and then high as you increase temperature. And why this happens is explained as such. When you increase temperature, you help electrons move easier, so it leads to higher leakage and smaller row hammer threshold. At the same time, it also makes traps lose their charge. If you have some leakage path that is assisted by some traps in your silicon, then it gets weaker, and then you end up having larger row hammer threshold. And the question is like which of these leakage paths are becoming dominant at what DRAM cell, at what temperature. And it highly depends on device characteristics. So it leads to a significant variation across cells, chips, and manufacturers. So our observations are already exploited in the field later on. So basically, if you observe row hammer bit error rate or DRAM rate disturbance bit error rate to measure change in temperature, and you find some canary cells that only experience bit flips at particular temperature points, then you can spy on some remote machine's temperature. And this is that paper that followed this methodology that I'm not going to go through, that exploited our observations later on. Okay, so another aspect of experimental findings is about memory access patterns. So before we did this study, this was the worst known memory access pattern for inducing read disturbance bit flips or row hammer bit flips. Basically opening and closing rows as frequently as possible so that within a given time window, you maximize the number of opening and closing operations that you perform. But instead of doing that, what we did is that we opened the row, and when you open a row, you basically put some high voltage on some metal layer, and it creates some electric field. And we wanted to see the effect of that, so we kept the row open for longer time. And when we do that, we observe that we can significantly reduce the number of opening and closing operations to induce a bit flip. And this has an immediate implication on defenses. If your deployed mitigation mechanism in your system is not accounting for this kind of effect, then you can bypass this. And then this finding also paved the way to the discovery of another read disturbance phenomenon called row press, which was published in CISPA in 2023. So this is a plot from row press. Basically, we observed that the opening and closing, so AC min is the activation count, the minimum activation count to induce the first bit flip. So on the y-axis, and on the x-axis we have the different times that we wait when we open the row. So on the leftmost column, you perform row hammer operation basically. You open and close rows as frequently as possible. And as you go right, you keep the row open for a longer time. And we observe that the minimum activation count you need to induce the first bit flip reduces significantly by 1 or 2 orders of magnitude. And if you go for like very extreme cases, which is not practical today, if you open a row and wait for 30 milliseconds, then just doing that is enough to induce bit flips. And this is a common behavior across modules from 3 different major manufacturers. And these are some results from DDR4 DRAM chips. And later on, we also repeated the same experiment on HBM2 DRAM chips and observed a similar behavior. With this reduction, so activation means opening here. If you open a row for a few hundreds of times in a 32 millisecond or 64 millisecond time window, then you can induce bit flips. And the scary thing is that this number is really low, because in that time window, you can do more than 1 million of such operations. And if you look at the spec workloads, even in those, you can find some applications that are doing this already. So the benign application actually becomes an attacker here. And it makes our all defense mechanisms more and more expensive. Okay, I'll talk about this row press a little bit more. But before that, I need to provide some more background. So inside the DRAM array, as I said earlier, like we organize DRAM cells as rows and columns as a two-dimensional array. And when we have access, so when you open the row, you pull the row's data to this buffer structure called row buffer. And you serve the column accesses from there. And there are three possible scenarios when you have an access. The first one is row hit. Basically, your data is already inside this buffer structure, and then you serve the I/O, the read-write commands from there. The second scenario is row miss. Basically, the row buffer doesn't contain any data, so you need to fetch the data from the row itself to the row buffer, and it incurs an additional latency as much as the read-write latency itself. And then you need to service the read-write requests. So this is the row miss. And the third scenario is a row conflict. Basically, another row is fetched into row buffer. You first need to close this row, which takes a similar amount of time as well. And then you need to open the row that you want to open. And then you can access data from there. So if you look at these latencies, you will see that there's a huge difference. And if you have a row buffer hit, then you will have significantly faster accesses compared to miss and conflict. And this is the key insight that the memory controllers use. And if they think that there's a higher possibility of accessing another piece of data inside a row, then they tend to keep rows open for a longer time. And we exploit this insight of the memory controller design. And we basically keep accessing different columns of the same row at different times and put more incentive to the memory controller to keep the row open on commodity systems. And by doing that, on this system, on an i5 CPU and this DDR4 module, we use this kind of code that I'm not going to go into details, but essentially we have different accesses to different columns in the same row whenever we open a row. And here in this plot, on the x-axis, we see like how many columns we read when we open a row. And on the y-axis, we look at the number of bit flips that we observe. The previous worst case access pattern was row hammer. So basically, you open a row, you access one column, and then you close it to open another row because you want to do the open and close operations as frequently as possible. Instead of doing that, if when we open a row, if we perform 2 reads, 4 reads, 8 reads, and sweep like this, then we start seeing bit flips after like 32 reads, for example. So this means that with such reads, we keep the row open for a longer time. That will cause a significant reduction in the number of activations needed, and we will see bit flips. And the reason that we don't see bit flips in these earlier cases is that the existing mitigation mechanism already implemented in the system is mitigating such bit flips. So this is basically a method of bypassing that in some commodity systems. And here is the same plot for the number of erroneous rows inside your DRAM chip. So it's not like these bit flips are not accumulated in a single row, but spread across. Okay. Okay, so the last piece of representative experimental find that I will share is about the variation inside the DRAM chip. So we characterize the read disturbance vulnerability characteristics of different rows inside the DRAM bank. And let's say this cartoonish picture shows all of the rows in your DRAM bank. And what we find is that, let's say we look at the weakest 10% of the rows, and we get the minimum activation count or minimum number of times that you need to open and close rows to induce bit flips. And let's say we need like n times of doing that for this weakest 10% of the rows. In the remaining 90% of the rows, we need double that hammer count. So it shows that this vulnerability significantly varies across DRAM rows, and configuring a solution for the worst case, for the weakest row, ends up making your mitigation mechanism overprotecting most of the rows. And this is quite costly, and I will talk about how to exploit this later on, actually in the next slide, to reduce the cost of the solutions. Okay, so here we exploit this this observation, the significant variation across DRAM rows. And by using this variation, we dynamically tune the aggressiveness of a given mitigation mechanism so that we can reduce its performance overheads. So our mechanism is called SVART, Spatial Variation Aware Disturbance Defenses. And essentially what it does is that if the row that is being attacked is stronger, then it performs fewer preventive actions such as refresh operations that are time costly. So a little bit more background. So this SVART is a mechanism that works in tandem with existing row hammer mitigation mechanisms. Here's an example of a row hammer mitigation mechanism called PARA, probabilistic row activation. What it does is that when a row activation happens, it generates a random number, compares this random number against a threshold, and it preventively refreshes the victim row based on this comparison. And we provide this information to SVART, and SVART dynamically changes the threshold so that if the row is more vulnerable, we have larger number of refreshes, or vice versa. And this mechanism works with any given redisturbance solutions today in the architecture level. So we tried it with several of them from the recent years. And we looked at the performance impact and showed that it significantly improves system performance by reducing the time you spend for such mitigative or preventive actions called refreshes. And it can be implemented at low cost either inside the DRAM chip or in the processor. And it improves system availability at low cost without compromising your data integrity. Okay, the last piece of the work that from my PhD that I'll talk about is addressing another issue that we call compatibility with existing DRAM chips. So a little bit more background again that you're quite familiar with. In the application level, we access memory using virtual memory addresses. And in the system level, these addresses are translated into physical memory addresses, right? And once you go to memory controller, these bits are parsed into smaller chunks to identify which channel of memory, which bank of memory you're accessing. And these all translations are visible within the processor. But once you provide the DRAM row address to the DRAM chip, this is a logical row address. And inside the DRAM chip, it's translated again to a physical address. And this is a proprietary information used for making the DRAM chip design much more competitive. And as a result, if you deploy a memory DRAM redisturbance mitigation mechanism inside your processor, and it detects an attack to row A, so basically what it does is that it issues a refresh command targeting addresses A+1 and A-1. And due to this address translation within the DRAM chip that is not exposed to the processor, then these rows can be in irrelevant locations. And in the actual victim rows, you still have bit flips. So this is a huge compatibility issue of like pretty much all the mechanisms before this paper. And here what we do is that instead of, since we do not know which victim rows, which rows are the victim rows after detecting an attack, instead of refreshing them, we selectively throttle the accesses that are targeting the row that is being opened and closed very frequently. And as a result, we do not need to know the addresses of the victim rows. We can prevent redisturbance bit flips without the knowledge of or modifications to DRAM chip internals. We looked at the performance impact of this as well, and if there's no row hammer attack in the system, no row is being open and closed very frequently, and as a result, we have small performance and energy overheads. And then if there's a row hammer attack present, the row hammer attack itself is consuming a lot of DRAM bandwidth. And once we throttle the accesses of this attack, basically we open up some bandwidth for the concurrent running benign applications. And it significantly improves the system performance and reduces the energy consumption. Okay, so there are some other words that I will not cover, but just show here. I have some longer videos on YouTube that you can find more details. But of course, before those videos, I'm happy to talk about all these details in person as well. So please ping me. Okay, and in the remaining time, I'm gonna talk about more of like my research after my PhD and future directions. But I'd like to give some story about that as well. So meanwhile, we were doing this. Industry also did some research on Rowhammer or DRAM read disturbance in general. JEDEC is the consortium or council that defines these protocols, DDR3, DDR4, DDR5. They formed the Rowhammer task force to address this issue. And manufacturers initially had some denial attitude. They ignored the vulnerability in the beginning, but then they moved to more solution-oriented approach with this Rowhammer task force. And we saw the one early solution from a French company called UpMem, which is a startup that is mostly known for their processing memory architectures, but this is the first promising, basically, study that came from them, and then we did security analysis of that. And then we started seeing papers from Microsoft, SK Hynix, and this one is from Samsung, and then NVIDIA. So all these companies are putting some budget and time to do research on this kind of topic. And later on, we also saw a Google paper that actually bypassed Samsung's solution, basically hacked it. And JEDEC over time released some documents as like guidelines for designers to implement Rowhammer mitigation in the system level or in a nearby DRAM chip. And later on, the first, in my opinion, this is a subjective opinion, the first promising solution or update from JEDEC came last year. It was about the time that I was defending, actually. This update to DDR5 standard proposed a new mitigation mechanism called PRAC, per-row activation counting in DRAM chip. And immediately after that, we went ahead and started analyzing the solution. And this is a paper that we published in the DRAMSec workshop that is collocated with CISPA last year. We showed that PRAC is secure against Rowhammer, and but it has some caveats. So in the common case, it reduces your performance by 10%. And in extreme cases, if you exploit the operations that it's doing and trigger those operations so frequently, then you can basically reduce DRAM chips availability by 94%. This is essentially the denial of memory service. And there are some details here, but I think I don't have much time to cover those. This is how PRAC works. Essentially, what it does is that it does both tracking and the detection, and mitigation inside the DRAM chip. So it puts a counter for each DRAM row, and it updates the counters as much as, whenever the row is activated. And to mitigate, it needs to perform some refresh operations. But by the nature of this protocol, CPU has fine-grained control over the timings of DRAM chip. And DRAM chip itself doesn't have time to perform these operations. So it sends a back-off signal back to processor. And processor provides some time to DRAM chip to perform such operations. So this is a nice addition to the protocol, but the devil is in this detail. The counter updates are the cause of such slowdown. So the key insight is that the proposed mechanism in the JEDEC document is that let's put counters inside each DRAM row. And whenever you access a row, basically you access the row to get some data out of it, right? So you do not want to postpone your actual read or write requests. And basically you you serve all those requests, and when it's time to close the DRAM row, you go ahead, read the counter value, update it, write it back, and it increases the time you spent for closing row by 140%, and it translates to 10% overhead in your overall performance. And to solve this, we came up with the key idea of leveraging some inherently available parallelism inside the DRAM chips that I can explain here. So this is the whole array in your DRAM bank. And internally, it's for performance reasons, it's split into smaller chunks of two-dimensional arrays. And each chunk of these two-dimensional arrays can perform some operations independent from each other completely simultaneously. And to leverage that, we put the counters in another smaller chunk that we added over there on the top. Instead of making the array larger on the horizontal, we went it vertical. And then this allowed us this parallelism so that we can perform regular accesses in parallel to counter updates. And this became an HBCA paper, another major conference in computer architecture. And it was published like earlier this month. Another problem was the denial of memory service. So we have another mechanism called break hammer for that. So in the memory controller level, we observe the row hammer preventive actions, and we trace back which particular hardware thread created or triggered this row hammer preventive action. We care about this because row hammer preventive actions are actually consuming some time. And based on this information, we suspect some hardware thread, and we slow down the memory accesses of these threads by basically limiting the number of missed status registers inside the cache hierarchy. And by doing that, we significantly improve system performance, reduce energy consumption when there's an attack. And when there is no attack, we basically don't have much impact on the system. And this became a paper in another major architecture conference, Micro, last year. Okay, so these are the main topics that I've been doing research after my PhD. And going forward, in the last 5 minutes, I believe, I'll try to cover some, like 3 directions that I'm planning to pursue. One of them is hardware-software co-design for sustainable robustness. I think I don't need to motivate you with hardware-software co-design. This is a direction. This is a method that is adopted by like many works to improve system performance, reduce energy consumption. But I believe that we didn't exhaustively explore the design opportunities for security purposes. Here's an example. So in the hardware level, we have very precise sensors, counters that can quickly and accurately identify what's going on in our system. Some examples are like we can detect this row hammer attacks that I talked about, or the performance attack that I talked about. There are some works that detect timing side channels in the hardware level. So these all things can be done in hardware level quite precisely. That software doesn't have that much details on hardware level events. But in the software level, we have the better big picture. We have the concepts of programs, users, address spaces. And we can, when we merge all this information together, we can have better malware detection mechanisms, and we can even push it forward to provide some constructive feedback to the programmers as well, to tell them that, okay, this piece of the code is creating this kind of trouble in the hardware level. So such cooperation can give us some beneficial directions. And there are more research, I guess, to do in that front. The second thing I want to talk about is data-centric robustness. So this is a screenshot of a slide from Bill Daly's talk. So when you look at the energy consumption breakdown of some systems in 2015, today I guess it's more radical. You observe that a memory access is consuming a very like 2-3 orders of magnitude larger energy of the arithmetic operations. And this is a major drive of the memory-centric computation for better performance per joule or per area. And today there is a huge drive in the computer architecture and system research to push processing memory and processing storage kind of solutions and explore the opportunities of these computation paradigms. And the security aspect of that is not really explored well. And the most common practices today we have about security are more of a taking processor-centric approach. And but when we look at like what these things do, we can actually perform many of them inside the memory, inside the storage as well. So I think there is more research that needs to be done on that side. And so there are some papers already exploring these options in the last years. So IceClave is an example, for example, in 2021. And then we have this Archronos paper in HPCA that looked at putting a specialized circuit inside the DRAM chip. And there is also some working on proposing some homomorphic encryption to perform homomorphic encryption inside the memory, inside the storage. And this is an active field of research that's going on, and I think there's more opportunities here. And another aspect of that is the security of the data-centric computation itself. Basically, when you do time inside and covered channels inside the memory or near memory, you have less noise, you have no caches or simpler caches that you need to bypass, and you have finer grained control over the memory accesses, and it gives you larger channel bandwidth. And unfortunately, there's no low-cost and effective solutions yet, so this is an active problem that this paper that will appear in DSN this year will show. Okay. So about the data-centric security and privacy, I'm particularly interested in critical health applications as well. So agent-based simulations and genomics applications are quite important. Again, my subjective idea or view for future of the humanity. And they have some common characteristics. They deal with excessively large amount of data. They use vastly shared systems for scalability. And their computation is distributed, and data integrity and confidentiality and privacy are some of the main concerns that they have. But when you look at the state of the art on those applications, the performance challenges are barely solved today. So people are still trying to make them work rather than providing security for them. So there's more opportunities that I want to pursue over there. Okay, and the last piece of the last direction that I'm planning is a better understanding of the failure mechanisms. So the generic question is, what is the worst case in my system? Basically, these failure mechanisms, like read disturbance is one of them, depend on many conditions, and they rarely occur or probabilistically occur, and it's quite costly to test every single piece for the worst case going forward. I know that I have 1 minute, but I will cover this. So the post-manufacturing testing is quite expensive because it postpones the shipping of your chips, and it's not really practical today. So they basically cover the common case rather than the worst case. And we need better methodologies and infrastructures to do that. One thing is that when you test your chip, it can be a processor, it can be a memory, you basically do it offline. And you need to obtain a lot of those chips for a statistically significant academic study as well. And my goal in the long term is to revolutionize this methodology of testing and data collection. Basically, I will come up with better online testing methodologies so that we can test our chips while they are running in the field, using their idle time or whatever. And we will have some automated reverse engineering tools to do the reverse engineering step without the huge burden on the user. And once we enable these, my ultimate goal is to crowdsource this data collection If you look at the gaming community, for example, there's a huge community that is sharing their results about like increasing their clock speed or voltage, and you can find data in like forums, Reddit posts here and there. So there's a huge community about that, but we need a more structured and well-maintained community to crowdsource more data collection from a field, so that this can give us the opportunity of covering the corner cases and the worst cases in a faster and more comprehensive way. So here are some examples of good offline testing tools, but we need plug and play runtime testing tools. And with that, I believe that we can achieve more reliable and more secure systems going forward. And I will just reiterate, my goal is to enable systems to robustly and sustainably scale as chips get denser and many users share systems. And that's the end of my talk. Thank you very much.